All right, in this video, I want to take a look at the answers from the quiz from the other day. Some of these problems I'm going to go through pretty quickly. There were some that got missed at a little higher rate that I'm going to try to look at perhaps a little bit more carefully. All right, with that said, let's take a look at the first one. The first one was sine of 15 degrees, and this one was pretty straightforward. You just needed to come up with a trig identity that involved a 15, and you could have done that several different ways. You could have done a sine of 45 minus 30 is probably what I would have done. And so that's going to be the sine of 45. This is using the sine difference identity. Sine of 45 cosine of 30. Remember, you subtract the two values when you're subtracting for the sine one, and you flip-flop the two angles. And then ends up being sine of 30 cosine of 45. And basically, you can just fill those values in. So sine of 45, hopefully you know that is radical 2 over 2. Cosine of 30 is radical 3 over 2. And then you're subtracting sine of 30, which is a half, times the cosine of 45, which is radical 2 over 2. When you work all that out, you're going to end up with a denominator of 4 for both of those fractions. So our final common denominator will be 4. You'll end up with a radical 6 when you multiply the radical 2 and the radical 3, and you'll end up with a minus radical 2 for the other one. And on this version of the quiz, you actually had a calculator, so you could have checked that answer in addition. All right, let's move on to the second problem here. Second problem was cosine of 57. I'll write this down. I'm not going to write the degree symbols in here. I really should, but it just makes it take too long. It's cosine of 57, cosine of 12. Then it was plus sine of 57, sine of 12. And so you might have noticed this one starts out with a cosine followed by a cosine. That's the cosine identity. Remember, the cosine identity is backwards for the sine. This is going to be a cosine difference identity. So it's going to be the cosine of 57 minus 12, which of course is the cosine of 45. And the cosine of 45 degrees is radical 2 over 2. If it's something that you can evaluate on the basic unit circle, go ahead and do that. If it's something weird like the cosine of 61 or something like that, then just leave it in that form. It should be pretty clear whether or not you need to evaluate it. Okay, the last in that section was the cosine of 22.5. It's kind of a weird one, really just showing that we understand how to use the quotient formula. So 22.5 is half of 45. So you can do cosine of 45 over 2. And the relationship there is that it's plus or minus. It's the square root of 1 plus the cosine of the angle divided by 2. And that 2 is under the radical. All right. So cosine of 45 is radical 2 over 2. So you'll end up with 1 plus radical 2 over 2. That's all going to be over 2. It's all under radical. The plus or minus doesn't mean you have two answers. Okay, you don't take sine or cosine and get multiple answers. What it means is, depending on the quadrant, it may be positive or it may be negative. Okay, this is a first quadrant angle. All the trig functions are positive in the first quadrant, so it's positive. Okay, if it was in the second quadrant, cosine is negative in the second quadrant, and you would make your result negative. By the way, this is not a great form. Really a better form to write this in, and we just didn't have time to make a big deal about this, but would probably be if you double the numerator and you double the denominator. You can multiply top and bottom of a fraction by the same value and you get an equivalent. So something like 2 plus radical 2 on top, and then the bottom having a 4 all under the radical would be good. Of course, if you take a radical, you're taking the square root of the numerator and of the denominator. Square root of the denominator would be 2, so it actually could revert back to 2. By the way, I didn't mention it, but number 1, sine of 15, 15 is 30 over 2. And so you could have done number 1 using the sine identity, which is actually the same thing, except it's 1 minus. It would have been 1 minus sine of 30 over 2, and you could have gone from there. And you would have gotten an answer that was in a drastically different form, but an answer that would have been equivalent to what I did in number 1. So I did see some people do it that way, especially coming off the quotient identities the previous class period. Okay, next one, they give you an angle that has a cosine of 5/13, okay, and they ask you to find cosine of 2x, okay? They do not expect you to find the value of x. Hypothetically, if you had a calculator, you could do that, but you'd be getting a decimal answer, and I'm asking for a fractional answer here. I'm asking you to use the identities. Okay, this is a double angle identity. Cosine of 2x. Remember, we actually have three different rules. You've got 1 minus 2 sine squared of theta. If you just have the sine, you've got cosine squared of x minus sine squared of x if you have both values. And the one we want, or at least I think the one that would make the most sense, is 1 minus cosine squared of x minus 1, since that requires only knowing a cosine and we don't have to go find the sine. Although the side's simple. You can make a little 5, 12, 13 triangle. It would be 12/13. Anyway, now remember, we don't need the angle measure. Okay, that I saw that a little bit on the quiz where people were trying to find the angle measure and they didn't know what to do. That's the cosine of theta squared. We already know the cosine of theta is 5/13, and in fact, now that I'm looking at this, I didn't did not write this well at all. Sorry, the cosine of x should be 5/13. I made it look like I'm taking the cosine of 5/13 there. So remember, sine, cosine, and tangent always have an input. It's cosine of something. Anyway, we just fill this in. You have a 5/13 in place of the cosine, and that cosine is being squared. And so it's going to be 2 times the cosine value squared minus 1. I believe you're going to get 50 over 169 minus 1. And you could turn that 1 into a 169 over 169. And I believe you end up with negative 119 over 169. I'm not going to spend a bunch of time on the video doing the arithmetic. I'll let you do that. But anyway, and by the way, keep in mind, this probably makes sense if that was a first quadrant angle. There's a pretty good chance if you double it, it's going to show up in the second quadrant. And I have an idea if you use an inverse cosine, you could probably figure out that was the case. Remember, cosine is negative in the second quadrant. So if you're a little bit bothered by that negative sign there, if you actually start thinking about it, if it was like a 65-degree angle or something, it would end up being a 130. When you doubled it, would be over in the next quadrant and would end up being negative. So that is what is going on there. Okay. Continuing, question number 5. Most people did not do what I intended, since I kind of rushed the quiz a little sooner than I was hoping to give it. I kind of looked the other way and took it. So a lot of people just looked at this and said, oh, you're just shifting the angle by 2 pi. That's going to give you the same sine value as just regular sine of theta. So most people got the answer right, that this is equal to sine of theta. It wasn't really what I wanted. I asked you to use an identity to show this. And actually, I think there were a couple of things where people did use identities, but maybe different than what I intended. What I intended you to do was to say, hey, look, that's a sign of a difference. So in other words, maybe you're on a test or a quiz and you think maybe you're allowed to use an identity, but you're not sure. And one of the values to knowing the identities is that you could use an identity to prove that some other relationship you wanted to use actually is consistently correct. And that's what's going on here. So if you're like, I think I can simplify this down to that. Well, you could actually go through the difference formula and you can show that, yeah, that really does work. So sine of theta, it would be sine of theta times the cosine of 2 pi. And then it's a sign difference. So it would be minus sine of 2 pi times the cosine of theta. And you're looking at that and you're like, well, how is that going to simplify down to sine of theta? But start evaluating things. Okay, I can't evaluate sine of theta, but cosine of 2 theta, if you think about the cosine function, cosine of 0 is 1. So cosine of 2 theta is also going to be 1. So that just simplifies down to sine of theta. Okay, if you go to the second part over here, sine of 2 theta is 0. 0 times anything is just going to be 0. So you have sine minus 0, which of course is going to end up being sine of theta. So that's what I had intended on number 5, although that's not always what I got on number 5. All right. Next one here. We've got the trig identities, and I think I'm going to do the longer ones on a separate video, but I'll do the short ones here. So problem number 6, we had cosine of t. These were all pretty quick, plus tangent of t times the sine of t, and we were trying to simplify that. Okay, and typically if you've got almost everything in terms of sine and cosine, I would just turn everything into sines and cosines. It's a pretty typical strategy. So tangent is sine of t over cosine of t in this particular case, and you've got another sine of t here. And on the surface you're looking at that, and of course that's the same thing as a sine squared of t over cosine of t. But I've got fractions, and if I want to add fractions, I could get a common denominator. I could multiply the top and the bottom of this fraction here by cosine of t. And of course, in the bottom, that's going to give me a cosine of t. And so what you see here, once you go ahead and multiply these, we end up with sine squared of t over cosine of t plus cosine squared of t over cosine of t. You add with your common denominator, it's all over cosine of t. What you end up with is a cosine squared of t plus a sine squared of t all over cosine of t. Well, sine squared of t plus cosine squared of t is just 1, okay? 1 over cosine of t is just going to end up being the secant of t when you simplify the whole thing. So, again, if you have one thing that's a fraction and one thing that's not, trying to get a common denominator and add your fractions very often is a pretty good strategy, all right? If we take a look at number 7, okay, number 7 gives you sine of x times the secant of x all over the tangent of x. And same kind of thing here. I'm just going to write everything as sines and cosines and see if I get any cancellations. There's no addition or subtraction here, so I don't have to worry about common denominators or anything like that. So I've got the sine of x basically over 1 by itself. Secant of x is 1 over cosine of x, so I'm going to write it that way. And I'm going to move the tangent to the top as a cotangent. Cotangent of x is cosine of x over sine of x. And notice, I can divide the top by cosine, we get 1. I can divide the top and the bottom by sine, we get 1. And anyway, everything here would just simplify down just to equal 1. All right, so that one hopefully was relatively basic for most people. I think I saw a lot of people getting that right when I graded the quiz. All right, number 8. So 8 is kind of weird looking and can be very tough if you don't know your trig identities pretty well. So it's a 2 plus tangent squared of x in the numerator over a secant squared of x. And then you're subtracting 1, okay? And, on the surface, you can try all kinds of things, but this 2 is going to keep coming back into play and causing kind of a problem. The thing that I noticed, I saw this tangent squared, and I said, well, 1 plus tangent squared is equal to secant squared, okay? 1 plus tangent squared of theta is equal to secant squared of theta. And so I thought, well, okay, couldn't I break this up here and make this a 1 plus tangent squared, 1 plus 1 tangent squared of x. In other words, get this, but have an extra 1 that has to be part of that too. And, isn't that something that, would be relatively simple to do? So that's how I broke mine up. So I broke it up as 1 plus tangent squared of x all over secant squared of x. And that is secant squared of x right there, okay? And then we're subtracting 1, okay? Well, to simplify this, it's a 1 plus secant squared of x all over secant squared of x, and then we're subtracting 1. One of the things that I do use a lot, you got to be careful about common denominator rules when you've got addition or subtraction. But if you've got addition or subtraction in the numerator, you can break that up as 2 separate fractions, both of which have the same denominator. So that's my thought here is I'll break this up as 1 over secant squared of x plus secant squared of x over secant squared of x. And then minus 1. And of course, this is just 1. You have to be careful. It doesn't cancel. Sometimes people say that it cancels to 1. But notice now we've got a 1 minus a 1 here. And the only thing we're looking at here now is the 1 over secant squared of x. 1 over secant squared of x, of course, is the same thing as the reciprocal cosine squared of x. And you've got your final simplified version there. So that one turns out to not be terrible if you pick up on that tangent squared and start thinking about Pythagorean identities from the start. And if you don't try Pythagorean identities, you might really spin your wheels there, or at least I think I would have. All right, so 2 of these to go, and then I'm going to do a separate video, I think, with the other part of the quiz. We've got a cotangent of x, we've got a secant of x, and it's all over a cosecant of x. And first of all, there are a lot of reciprocals here. You may want to flip all of these. You could actually move the cosecant x to the top as a sine of x, and you could actually move the secant of x to the bottom as a cosine of x, and you could actually move that cotangent of x to the bottom as a tangent of x. I don't think you necessarily need to do it that way, but you could. Anyway, I'm actually not going to do it that way, but I just want to make the point that you could. It might be an alternate method that quite a few of you used. I'm actually just going to write everything out using sines and cosines, which usually works out pretty well. So cotangent is cosine of x over sine of x. Okay, secant of x is 1 over cosine of x. And I think I'm going to move the cosecant to the top as a sine of x, because that actually seems like it would be pretty convenient. And this is all being multiplied. Okay, sorry, that looks a little bit like a subtraction there, but that's multiplied. So I can divide a sine out of the top and bottom and get 1. I can divide a cosine out of the top and the bottom and also get 1. And so, yeah, that whole product is just going to simplify down to 1. So probably shouldn't have had 2 answers of 1 there. And be careful, you could get a negative 1 or something like that too. But anyway, that's all that's going on there. All right, number 10. Number 10 was missed a lot more than other ones, and this might be one that I come back to in class just because it was so consistently missed. So remember, we had a bunch of additional identities that we talked about. We had the cofunction identities, like sine of theta and sine of the complement of theta. So like, I'm sorry, sine and the cosine of the complement of theta. So cosine of like 90 minus theta, that kind of thing, are going to be equal to each other. We also talked about even and odd functions. Remember that odd functions are symmetric about the origin, which means, for example, if I have a function with f of 2 equaling 8, f of negative 2 will equal negative 8. In other words, if the sign of the input changes, the sign of the output also changes. So we say that f of negative x, in other words, if you flip the sign on the input, it flips the sign on the output. So we say that f of negative x is equal to negative f of x. Okay. And good examples that would be like y equals x cubed. The tangent function is a good example. Graphs that are symmetric about the origin. You can reflect this over the x and y axis, and you can get the graph reflecting onto itself. Okay, that's an odd function. Even functions, if you remember, are symmetric about the line y equals x. Sorry, about the y-axis. And so a good example there would be y equals x squared, for example, y equals x to the 4th. The cosine function is a good example of a function that has symmetry about the y-axis because it does this sort of thing. So anyway, the sine function, meanwhile, is an odd function. I mentioned the tangent function being odd earlier. Anyway, big idea being here that regardless of the sign of x, the y value is not going to change. Like, for example, if it was y equals x squared, f of 2 would be equal to 4. If I change the sign and I go over here and look at f of negative 2, f of negative 2 is also going to be 4. Okay, in other words, if you change the sign of the input, the sign of the output does not change. And in symbols, the way they write that is that f of negative x is equal to just regular f of x. Okay, now what does that have to do with the quiz? Well, on the quiz, I had something that involved even and odd functions. We had a statement to simplify. It was tangent of theta plus cosine of negative theta plus tangent of negative theta. Okay, and so a couple of things here. First of all, tangent is an odd function. Okay, it does this kind of thing. Now remember, it's got asymptotes, so you've got those lines coming there. It's a little hard for me to draw on here. But anyway, if you change the sign of the input, it's also going to change the sign of the output. So, for example, the tangent of 45 degrees, tangent of pi over 4 is radical 2 over 2. Sorry, no, it's not. It's 1. The tangent of negative 45 or negative pi over 4 is negative 1. Okay, so tangent of theta here, tangent of negative theta is the same thing as the opposite of the tangent of regular theta. Okay, so changing the sign of the input is going to change the sign of the output. Okay, so anyway, long story short, if I've got a tangent of theta and I have a negative tangent of theta, those two are going to cancel each other out when we add them together. Okay, now we come back to that cosine function. Remember, cosine is an even function, and because it's an even function, it is symmetric about the y-axis. It does this sort of thing. And so cosine of negative theta would be right here, for example, maybe, and that's going to be exactly the same value as cosine of positive theta. So cosine of negative theta, I suppose you could leave an answer of cosine of negative theta, and that'd be okay-ish. But what I was really looking for you to do is to simplify that down to cosine of theta. Okay, so for those of you who are interested in seeing answers for the second part of the quiz, which I suspect is where people are going to want to see answers, I'm going to make a second video, and you can see that for the back page of the quiz. So I hope that helped on page 1.